So, hello, I'm Gorka Guardiola, and I'm going to present some work that I'm doing with Enrique Soriano. We both are Plan 9 old-timers, but we didn't do this in Plan 9, and then we ported it to Plan 9, so let's see how it goes. So, the name of the thing I'm presenting is called Socarrat, which is actually the rice that gets singed on the pan when you do a paella. And it's really difficult to clean, and that's where the name comes from. So in this talk, when I talk about the file system, normally for any other audience, I wouldn't have to clarify it, but I'm talking about the data structures that you actually write to the disk, not the protocol that you use to export stuff or the API that you have on, to actually deal with files. Actually, I'm talking about X4 or XFAT, which will. So what we wanted to implement is a kind of worm, which is a write once, read many. This should be, if you are familiar with the old dumps in Plan 9 or with any of the other file systems that provide this kind of service, it should be clear what it is. It's something that you can write but not delete after it's written. And it's good for backups, but also for logging what happens to the system. So the problem is, how do you actually guarantee that something is not deleted after, and against whom can you guarantee it? So having a worm is actually a kind of security guarantee. Especially if you have the logs where you write, whatever's going on in the system, and then you get an attacker, and the logs capture traces of the intrusion, and then the attacker at some point escalates privileges and tries to delete it. How can you actually guarantee that it's not deletable? And so we wanted to write a worm for logs, so it's specialized for append-only files, which cannot be deleted after. And there are two essential ways of providing a worm. Like, one is specialized hardware, and this is how it used to be done in old-time Plan 9, where you have this jukebox, this optical jukebox, which can be just written, but it cannot be deleted. And there's the software way of doing it, like Fossil or any other subsequent Plan 9 file system that lets you have a kind of worm. There's a third way of doing it, which is distributed, but that's not a solution for us, because then you are moving the problem somewhere else. And I'm not going to go into blockchain, which is the first thing that people say. So this is for in case you have an intrusion. The first thing, if you are doing your logging outside, the first thing the intruder will do is run some kind of denial of service for your network, and then you won't have logs. So this is like the original worm device, which is a continuous printer, and it's still used in some contexts. It's actually a very good model of the guarantees we are going to try to provide. So you can break the printer, but what's printed is printed. And that's the main guarantees I'm going to talk about. And there are other ways of doing worms, like linear tape that only goes forward, and jukeboxes. The problem with all that is that they are either cumbersome or expensive, or they don't sell them anymore. We wanted to do this with software, but providing the guarantees of hardware. And this is the difficult part. Remember that we want to provide guarantees in the case the system is totally compromised. This is a very strong guarantee. We did a file system before called SealFS that provides tamper evidence in using cryptography. So you can actually modify the logs, but you will be able to check if they are modified. The way you can do that is essentially having keys and deleting them after signing the logs. So you have like a key stream. You can generate it with a ratchet or other ways. And you keep the keys offline, and then you keep consuming keys and signing the logs. And that's the way you can provide the guarantee that even in the total compromise of the system, the attacker cannot go backwards in time, because what's signed is already signed. And they can create logs for the future, but you have the time component where logs from the past cannot be modified without being detected. But this is not enough, because we want to provide the guarantee that what's written cannot be deleted. So that's why we built this Socarrat thing, which is a local worm device. The main constraint is that we wanted it to be able to use in any conventional machine, even any OS. So it's a device that you have to plug, and it's a worm device that you can use Windows, Linux, Plan 9, Mac OS, whatever. And in order to simplify our work, we specialized it to append only log files. And as an extra, we wanted it to be also tamper evident using the work we did before. And we wanted to be very, very cheap. That's the main thing. So our original prototype was a Raspberry Pi 4, which is like $69. And the new prototype, which is USB 3, is Raxda 4C+, which is similar price. So that's So what are the guarantees that we want to provide? As I said, they are inspired in a continuous printer, so we call it the continuous printer model. So once committed, you cannot delete. You can write data, but you cannot delete it. If you have some sort of cache or anything between you and the data, you have to actually, now and then you have to write. You cannot just, so if the machine turns off or whatever, you don't lose too much, because you have to, there's some kind of liveness warranties. And the most important one, once you print, you cannot delete or modify, or you cannot undo the write. So how do we do this with just software? So the main idea with this is what we call a reverse file system. So our device presents itself as a block device. So it looks like a hard disk. So when you write to the file system, you write blocks to the hard disk. And our device, actually, it's an intelligent hard disk. And what it does is it looks at the blocks as they are coming by, decodes it, and tries to understand what you are doing to the files, and then keeps separate files for the files that are interesting to you. So you write to an append-only file that writes to the block. Then you see the block, and then you deduce what you were trying to do to the file and keep a separate file. So the attacker has no operation to delete that file because they didn't create it. You can only append to it. No, this is a strange idea, but so how we did it originally in Linux, we have this Go component that serves a socket that serves a block device. We export that using USB on the go, and then we mount it, and this is the user machine. This can be completely compromised. But the attacker cannot actually access these files, which are created and appended only to by looking at the blocks as they go by to the file system image. And this actually looks much simpler than it is, because when you are updating a file system, there's no guarantee that the metadata and the data comes in order in any way. So you have to know at what point you are sure that, for example, if it's an inode-based file system, the inode and the tree under the inode are consistent enough that you can actually update the files here. So what happened is we have this working, and then Ron sent me an email. Are you coming to IWP9? And then I thought, so this thing here is a protocol called MBD, which is a protocol that appeared in BSD or Linux. I'm not sure.
Early 90s.
Yeah.
Yes, very old.
Which is for sending blocks on a wire. And I thought, if I wanted to port this to Plan 9, how difficult could it be? So if I export this part using 9p, so that's what I did. So I wrote a little part of this component that exports it as 9p with two files, a COTL file and a disk file. And then you can mount this, and like the whole thing actually is easy to port. We still have some parts to implement, so that's why it's a work in progress, because there's no USB on the go in Plan 9 yet. And CLFS is unimplemented, but that should be quite easy because it's much simpler in Plan 9 than that in Linux, because you just have to look at the writes in 9p. That should be this is like very easy. So another thing that I didn't talk about, as it is now, the reverse file system only supports X4 and XFAT, which have different compromises. This doesn't matter because you just create the image and export it, and you don't have to, like, the whole Socarrat doesn't have to have any other implementation of X4 or XFAT. Like the implementation is the reverse file system, and that's it. And there are different compromises on those. So I'll talk about that later. But in Plan 9, you preformat the images somewhere else and you serve them. And so the difficult part about this is, at what point are you sure that the subtree of the file system that you care about for the file is updated enough that you can actually look at it and make sure that it's there? So this is a different problem for X4 and XFAT. And as an aside, X4 has journaling, so in order to make sure that the file system is consistent in the case of loss of power, whenever you write to the file system, you first write to the journal. And the journal is a circular log where you write the operations, and once you have updated the file system, supposedly you actually advance the log. So you keep the operations that are open so you can undo them in case of a loss of power to a state where you have a consistent state in the file system. And there are two guarantees that you can give. One is if you are journaling metadata, that in case of a loss of power, your metadata is not broken. And the other guarantee you can make is that there's no spurious data in your files. And in order to do this, you have to actually journal the metadata, and in order to do this, you have to journal the data. X4 has different modes, and they don't provide the guarantees they say they provide sometimes. So this is a little bit more complex than it looks, because they say that there's some mode where they say they have flashed the data before the metadata, but it's not there. So one interesting thing about this reverse file system thing is that you can actually check if the people are providing you with the invariants that you want, because you are on both sides of the file system. You can write to the file system and actually check what's going on in the journal. But so So what we did, well, for exFAT, it's really easy. It's a very simple file system. Actually, if the people from Microsoft actually removed all the CRUD that they had, like for x32, x16, x whatever, and exFAT is actually quite cleaner. So it was very easy to implement. But then, but there you don't have a journal. They have like some transactional FAT thing that no one implements. So what we did is we had this idea that if enough time has gone by since you started writing to the disk and your file system is not completely broken, supposedly things have ended up in the place where they should be. So we just have like a coherent time window, and we wait from the first write you do to the file, we wait, and then we supposedly the tree is there, and it's actually there. So we also do another thing to try to provide these guarantees, is that we zero the disk. So there's some extra things there to try to be as coherent as possible. With X4, we actually use the journal as much as possible. So the thing with the journal is when you end up the transaction in the journal, at that point you supposedly know that you are at a coherent point in the file system. So you can actually look at the thing, at least with respect to that transaction to the files. I can't go into that much detail, but so we are doing all this, and now we are at the point where we can not only keep these separate warm files, but we can actually detect that people are doing bad things, because the attacker can actually try to modify files that shouldn't be modified at points where they shouldn't be modified, and because we are seeing all these transactions, we can have policies to. So what do you do if you detect that someone's trying to delete the start of a log that should be append only? And well, there are actually two things you can do. You can give back an IO error, and then funny things happen because some people in the chain may or may not ignore it, because there's, depends on the operating system, the USB stack, and well, you may be unlucky or not. We can actually reset the USB thing and export it again only read-only, or we can do another thing, which is keep the things they are trying to delete around and the new writes around to audit it after. So we call this a honeypot policy. So the attacker thinks they are writing to the files or and we keep it separate. We are still trying to find the balance for that. And so what we learned, it was very interesting because we had already the thing working with MBD, and then we wrote a separate transport for 9P, and so 9P is synchronous, and that means in some sense it's much simpler, and everything that we needed was semantically specified, which doesn't happen for NDB. I mean, it's the other part is that because it's synchronous, either you have a lot of operations in flight and then you waste a lot of memory to be able to do things fast, or you are slow. That's the thing. So there are compromises here that are interesting that we've been dealing with for the last, I don't know, 20 years. But in any case, it was very, very interesting porting to 9P because different ways of behaving with respect to synchronicity, different sizes, we uncovered a ton of bugs. So it was really, really useful for us because we uncovered many, many bugs. Someone yesterday said that the v9fs was very buggy. I didn't see that. I mean, it worked very, very well. There were a couple of things so we are exporting a file, and in Linux you have to convert that into using the loop device into device, and that means that all your writes are in chunks of 4K, and I'm not sure how to undo that in Linux, but whatever. In Plan 9 is no problem. Like you can write, you can use the file as a device, and you get writes of any size. So, and the library we are using, which I can't remember the name, but it's like the most popular 9p library in Go, has a random limit in the IO unit of can't remember how much, but it was a very small limit that didn't make sense. So maybe later, if I don't know, can't remember the name of the library, but if someone knows who has written it and why there's limit, maybe we can talk about this later. And for the future, in Plan 9, maybe implement the missing pieces. The most difficult part is USB on the go, which is an interesting thing for Plan 9, maybe. One thing that we notice is that USB on the go is 3.0, USB 3.0 on the go that works is very difficult to find. For some reason. I don't know. Supposedly in the future, all the ports are going to be USB on the go because of the new standard. But people randomly disable it. For example, all the ThinkPad laptops have USB on the go. Disabled for some reason. There's a hidden menu in the BIOS where you can actually enable it, but it's hidden, so you can't. I disassembled the thing and couldn't figure out how to put it to enable it again. Anyway, we could also do a reverse file system for other file systems. I don't know which ones or how, but and we have other ideas of doing this stackable, where you stack these things and you can add different stuff to it, like cryptography or whatever. And so I think that was it. Was I on time? I'm not sure.
That's very good. Thank you.
So questions?
Yeah, we got 2 or 3 minutes for questions. I've thought about this problem myself. Have you thought about using transparency logs on the secure side?
Transparency what? Sorry?
Transparency logs.
What is that?
I
I haven't, because I don't know what that is.
I completely agree with you that blockchains would be useless for this, and 95% of the companies that use blockchains, because they heard about it and were they thought the append-only properties were appealing, they should actually use transparency logs instead. It's just that very few people know about them and the properties.
So what's a transparency log?
It's an append-only. It's an authenticated data structure. It's append-only, and it's used to make digital signatures discoverable. So you change the trust policy from one where the digital signature accepted by a verifier is only for authenticity, to one where you the signature is also submitted to a transparency log, and you receive an inclusion proof, which is signed. And I can explain this.
You are talking about the distributed system.
You can do it locally as well.
But so if you do it locally, so if you do it locally, you have to do it with public key cryptography.
Not
because
necessarily.
where's the key? I mean, this is there is a total compromise of the system that you can.
Right, and it would be on the. I know how you could do this.
I mean, you can have a key, a secret key in some kind of trusted hardware,
right.
But that's when I say total, I mean total compromise of the system.
Yeah. Oh, no, I completely agree that you need USB device and so on. What I'm saying is that uh, well, it might take a while to explain.
Okay,
but,
we can talk after. Yeah.
Let's say this. I've been designing a transparency log for 4 years, and
Okay.
so yeah.
So you said you're essentially trying to figure out what is being written to the file system based on the blocks that are being
Yes.
sent to your device. I'm wondering how this interacts with, for example, let's just say I have a VM that has a disk image, and I'm writing to blocks in the virtual disk on the real disk. So I have, or for example, I'm an attacker and I want to fool you into filling up all your space. So I write to a file on disk and try to make it look like I'm generating file system metadata by filling a data file.
So that the simple answer there, I think, if I understood the question correctly, is, if I can find it, you can break the printer. That's not in the guarantees.
Yeah, I guess what I'm trying to figure out is more, I can generate writes to a data file that look like the writes to a file system. Is that something that you've considered?
No, you can't really, because I don't look so. I don't look at the blocks isolatedly. I have an idea of how the whole file system is. So every time I see a block write, I actually walk the whole thing. Some of it is cached because it should be modified in the future, but that's the.
Have you done a performance comparison between NBD and 9P?
Yes, a 9P is slower.
Why?
There are the simple and fast answer is there's no streaming in it. That's
But you can parallelize the requests.
yeah. But then you consume a lot of memory, and there are balances there where you start being slow because you don't have enough memory, and you have to wait for memory to be available. And there's a lot of stuff there but our first prototype actually was, so this is when you are running the tests locally on the machine. But when you are actually using USB, the first prototype was slow because we didn't know at the time the Raspberry Pi only has USB 2.0, and that's slow as hell. But now with the new machine, I got it working like a week ago, and then I had travel and exams and a lot of stuff that I had to do, so I haven't been able to measure it yet, but yeah.
So I see you were using NBD when you were setting this up with Linux as network.
But NBD and NDB, I'm very confused. So it's a protocol, yeah.
Yeah,
I don't know which one is which because my
NBD
brain.
network block device.
Yes.
So you say you switched to 9P. Did you consider something like ATA over Ethernet, which Plan 9 has support for?
No, I didn't. So. I don't know. It may be another protocol that we can support. I haven't thought about it. Yeah, could be.
All right, so one last question, and then we need to continue. The internet is asking, why don't you just use a DVDR?
A DVDR. Oh, so because there are multiple reasons, but how big is your DVDR, and how many times do you have to change it, and do you want to go there and change it? And I can have like I don't know how many terabytes disk these days.
All right. With that, we will need to conclude. Thank you very much.
Thank you.